Okay. So anyway, for this class, what that means is I will be, um, I'll still be here 9:30 Mondays and Wednesdays as usual. If that time ends up not working so well for people because of kids, um, school schedules and stuff that they have to start meeting with, then we can do something else. So Kimmy asked about a pass fail option. Yeah, I mean I'm not opposed to that. I think that's that we have to keep in mind that we've got, let's see, this would be technically week 11 of the semester, so we basically got 6 weeks of stuff to do. Um, we have to kind of assume, I know that there's people in this class who work in healthcare, who are going to be working more hours, who are going to have other stuff to do. There's always the possibility that any of us get sick and basically can't do anything for uh, a week or two or something like that. I think we have to plan for that as well. So my plan is to back off the schedule. We're not going to cover as many chapters as we originally had in the syllabus. I think that's fair. I think we have to meet the outcomes of the course, but not necessarily each objective of the course. We'll still be doing the weekly quizzes, and we'll do another exam and the final project. I What was I going to say about that? This exam I think went fine. We'll do the other thing. We'll do the next exam the same way. There should be, hopefully Harper is going to work out some more stuff in terms of like tutoring access and that kind of thing. I'll still be available for more office hours. How do we do as a class on the exam? So yeah, the I don't know the average actually. I'm not sure the average matters a whole lot with the class being as small as it is. Um, as with the last exam, I would say nobody totally bombed it. Everybody's doing okay. I don't see anybody in major danger of like failing the class at this point. So, that's good. I think keep going with that. There were definitely a few exams with some very, very similar wrong answers. So I'm not sure that the whole like don't work together, don't collaborate on this exam idea was followed. So I'd ask you to do a better job of that in the future. The Yeah, so if there's no tutoring, then well, especially if there's no tutoring, but either way, I can definitely do video office hours. So we can work out a schedule for that. I can be more flexible with the schedule also. So maybe what I'll do is send out some sort of a questionnaire, um, like a poll, so that you can select what best times. We can find some times that work for everybody in the class, so that we can do video office hours. We can do them in the evenings. We can do them, on weekends. We can do it, whatever, whatever works best between you all and my other classes, so that I can be available to help you out when you need it. For now, until that's done, just email me and say, hey, I need some help. When are you available? I know I've met a couple of you before spring break, and that worked out fine. So just let me know if you need that. Um, but yeah, back to Kimmy's question about pass fail. So that's discussion. That is a discussion that we're having on campus of, what does it mean to evaluate people in this format? What Everybody in the world right now, education-wise, understands that this semester is going to be a little bit weird. The state community college board has said that everybody should accept credits for this semester regardless of what we do in terms of lab requirements, that kind of thing. We're going to do some sort of lab activity, like where you have to take some data and do some stuff with it, but I don't know what that's going to look like necessarily. And you still have all of your lab notebook work, hopefully. So I'm going to get you a place to submit that on Blackboard, so I can still give you credit for all of that. I don't want anybody to do worse in this class because of this format than they would have otherwise. So that's a big guiding principle for me. I think if people do a little bit better than they would have otherwise, that's something I'm okay with. I'm more okay with that than somebody being really like penalized or having a big problem in the semester just because of circumstances beyond our control. So we'll keep in communication about that. If you're having troubles, I know some people have had some internet issues, things like that. Just let me know, and I'll work with you on that and try to figure it out. The final project is the research paper, right? And I'll keep that the same as what we've talked about, just because I don't want to change things up too much. So we'll keep that going the way you've been doing it. Everybody's picked some good topics for that. If the only thing I would say now is if you don't want to do that, or if you had decided not to do it, I would really encourage you to do it, just because we have limited other stuff. But if you did okay on this second exam and you're not really worried about it, and the whole thing is kind of working for you, then just stick with however you're doing it, and that's okay too. All right, any other questions before we get into the exam? I just realized this is not exam 1, this is exam 2. Yeah, so quiz 8 is due on Wednesday, and there's no final questions. I think what I'm going to do, because there was this, because I'm still having issues getting the other final questions up, I think we're going to do that separate. We're going to find some way to do that as a separate thing, where you submit some final questions at different times, and it's not part of the quiz, and it's not as required, and it's more for like to try to help with the final. We'll see about that, because I know people spend a lot of time on those questions for those other quizzes that they were on. Yeah, I will. I'll open up assignments, and I'm trying to get everything planned out so that it's all up on Blackboard for the rest of the semester, and there's fewer surprises. But I kind of wanted to wait until we have this meeting tomorrow and figure out some more permanent things. Same due dates for the research project. Yes. Yes. So I will get those up on Blackboard so that you can submit them. The only difference is we changed this last week, but it may still be different on the schedule, is that the annotated bibliography is due a week later than what it says on the syllabus. So I'll get that on Blackboard so you can see that. Oh, and if you emailed me last week, something happened with my email at some point, and a bunch of stuff got lost, and then it all came back, and I got this massive load of emails. So I probably have it. I'm kind of going through the backlog right now to see what I missed, but if there was anything urgent, send it again, because there were like 3 or 4 days when I didn't get stuff, and then it all came in a big batch. Okay, good. I answered your question. All right. So this exam, let's take a look at it here. So can you see this whole page? It looks slightly cropped or something on mine, but can you see the whole exam page? No. So you can only see like a snippet of it? The first and second question, yes, that's correct. But can you see from like the left side all the way to the right side? Like, can you see the question? Okay, good. Okay, because it's like cut off for me, but I think that's just because of how I have the chat thing. All right. So the first page here, completing some reactions. This one, for the most part, went pretty well, but there were a couple issues. Remember that, will I post this corrected online? You mean the exam itself? Like with the answers? Yes, I can post that. All right, so the first one, we've got HBr adding to the double bond. So one thing that I saw in the exam was people kind of mixing up the idea of drawing products and drawing mechanisms. And the mechanisms where you draw the arrows and like figure out what's happening in which step, that can help you to determine what the product is. But a question like this is really just asking for the major product, like what is the thing that happens here, or the reagents that are used in the transformation. So this one, most people got this. Remember HBr, the H is going to go to the less substituted side of the alkene, and the Br goes to the more substituted side. Here, we're asked for the reagents that will do this, so we have to be a little bit careful because the stereochemistry is specified here. This has to be SN2. So we have to put in reagents that are going to favor SN2 rather than E2 or SN1. So the best way to do this, as we talked about, and we'll review a little bit more today, is to use a neutral nucleophile like NH3. We would not want to use something like NaNH2 because that's a really strong base, and that would favor elimination. Remember, really strong bases favor elimination. That base is so strong it can deprotonate an alkyne. So we want to make sure that that one. So the better choice here is NH3. I don't think I took off many points if you said this one, but this is a better choice. And then really just ammonia, even though that would be a weird reaction to do anyway because of properties of ammonia, may not really be SN2 because it's really protic there, right? So that could potentially give us some SN1 problems where we could have some carbocation shifts and all that stuff. So if we really want to force SN2, we should also make sure to do this in some sort of a polar aprotic solvent, such as there's various ones, but let's say acetonitrile, just something from the list in the book. Right. And going forward now, I'm going to assume that this class is always basically an open book class. So the next exam or the next quiz will be open book, the next exam will be open book. The final, I think that works actually really well for things like this because you still have to be able to think about this stuff. You still have to be able to figure it out, but you can always look up reagents, which you would be able to do in real life anyway, right? If you didn't know what a certain reagent did or what the formula was, you could look it up. And so when you're doing these exams, you should look up the reagents, is what I'm saying. If you're not sure like what type of solvent to use, you can look that up in the book. All right. Oh, a couple more people are waiting to come in. Welcome. We're just going through the exam here. Sorry. Make sure everybody gets in here. Okay. Welcome. All right. So then here we've got another alkene addition reaction. So this was one, again, that, if you weren't sure what this type of a reagent did, you could look it up. This gives you the anti-Markovnikov or the opposite selectivity of adding water across an alkene. Right? So that's the product with the correct selectivity. Again, stop me if you want me to go more into some of these. Post a message in the chat or just jump in with voice, unmute yourself. All right, so then here we've got a situation with a tertiary carbon. And that means that we're going to have this competition between SN1 and E1, and there's really no way to pick one or the other. What happens here. So the SN1 product is going to be the substitution product with substituting for the nucleophile. And then that nucleophile is going to get deprotonated because we always have generally a neutral product at the end. So that's going to be OCH2CH3. Okay. Make sure that you're showing that the O is connecting there. And then our elimination product. Our elimination product is this one. There is a second less favored elimination product that I saw some of you listing. Right, that's going to be a minor product. You don't have to have that there for the answer because we're always talking about the major products, but that is a minor product there that will sometimes come up if you're really doing this experimentally. All right. So then here we've got addition of water. So there's two possible answers here. One answer is a little bit better than the other. So the best answer is this one. So we're adding water to an alkene. And actually, I don't think anybody picked this answer. The reason this is the best answer is that it is the most selective. So you've got basically a tertiary carbocation versus a primary carbocation. So the most, it's definitely going to go there. There's no chance that any water is going to go there because there's such a big difference between primary and tertiary, and the tertiary is always going to be favored in a alkene addition like this. Most people picked something like, let's see, where can I fit this over here? Either this one or this one. This one is probably the second best answer because then you've got this again, tertiary versus secondary. The tertiary is going to be favored, and so you're going to make that carbocation. The reason this is not as good is because again, we have tertiary versus secondary, but the secondary is still going to form a little bit, and then you could actually get a carbocation shift, and you could end up with this tertiary one instead, which would definitely not be what you wanted. So you'd have a whole mix of possible alcohol products on this one if you pick that one kind of by accident. So so this is the best answer because of the biggest difference in selectivity. You're definitely only going to make that one. I accepted these as well this time. All right. Just a second here. I need to. Is there a question? Okay, I'm back. Good. All right, so this one, the correct answer here is that you reduce the alkenes over here, but you don't reduce the aromatic. The aromatic is basically too stable to be reduced by hydrogen. That's actually something we're going to look at in a couple chapters in more detail. Why? Wait, you can't see the other options that I drew? Where? Over here? Those get cut off? Why is that happening? Okay, let me see. let me zoom out on it a little bit here. That's not helpful. Can you see it now? So a little more. So those are the two other options there. Okay. I wonder why that's cutting off because I can see it either way on mine. All right. Well, thanks for letting me know. So if I just leave it like this, you can see everything. Okay. Good. All right. So then moving on. This structure, we've got definite SN2 type conditions here. So we've got a strong nucleophile and a aprotic polar solvent. So we're going to SN2 displace that bromine. A couple of issues that I saw here grading these. So one, remember that SN2 reactions are not going to affect the rest of the molecule. So I saw a lot of molecules where this was gone, or the stereochemistry was switched. You can't affect some other side of the molecule. The only thing that's happening is we're attacking this bromine right here. So this is going to invert the configuration because it's SN2. And then we've got our nucleophile replacing it here. So the nucleophile replacing here is SCH3. So some of you saw this as like almost an ionic compound, like NaSH or something. This is not ionic. This is just like methanol, CH3OH, but with S. So this whole thing acts as a nucleophile, and then it gets deprotonated at the end. Right. So I saw some where it was just S or SH here. Make sure that you have the whole SCH3. That's the whole nucleophile there. All right. So then the starting molecule here. I didn't have you do the ending molecule because we don't know how to name these sulfur compounds, but we can certainly name this. So we'll go 2 bromo 5-methylheptane. And then we also have to make sure to put in our stereochemistry. Right? So this is going to be 2s 5r. So this carbon is S and this carbon is R. Okay. So here, this time, I gave you some reagents, but then I also specified exactly what mechanism, which product I was looking for here. The E1 product here, the elimination product, will be this one. If you drew the SN1 product, the substitution product instead, I mean, I gave you some credit for that because that may be a competing reaction in this process, but like I told you specifically what mechanism to use there. Here we've got bromination. So this time, because it's a stereo-specific reaction, we need to make sure that we're specifying the stereochemistry. And you can either draw both of them or write like plus an enantiomer, as we've done a couple times. And then the product, you can either name it SS and RR, which are the two enantiomers that are formed, the SS enantiomer and the RR enantiomer. Or in this case, you could also call this trans. Trans 1,2-dibromo cyclohexane. All right. And then we've got, excuse me, over here. We've got a elimination reaction, right? This is potassium tert butoxide, which we know is an extremely good elimination base that will be very selective toward the most open or the most unhindered hydrogen to deprotonate. So this one, again, we have a couple different choices, and there's one that's definitely better than the others. So we want to make this double bond, which means we need to put a leaving group on one side of it so that it can do the E2 elimination. So that can either be here or here. And one of those is better than the other. The answer is that this one, you can pick whatever kind of leaving group you want, but that spot is going to be a little bit better than the others. Can anybody say why? You can jump in with voice or just type it. Why is that better than having one over here? Than putting the bromine over here?
Isn't it because it's like less hindrance?
Yes. So the base then will definitely deprotonate here and make this rather than this side, right? Because in a ring like this, or really in any structure, you always have two choices where that bond is going to go. It's either going to go to one side or to the other side of where the leaving group is. So to the carbon on like over here or the carbon over here. So the bigger difference you can make between those two, the more likely it's going to go where you want. So this is going to deprotonate the less hindered spot over here rather than the more hindered spot over here. If we put it here, then both sides are basically the same. We've got the same kind of situation going on both sides. So we would expect that not to be very selective for like which one it's going to make. So if we did the other one, we would expect to make like this also, right? This one also, or as a separate possible product. So it's a little more selective if we put the leaving group there. So when you're thinking about these reactions in general, we've seen a few examples of this now. Think about what else could possibly happen with these reagents. If you're filling in a starting material, and then as you're checking your answer, think about, okay, well, where else could this react, or what else could happen? And make sure you're accounting for those things in what you choose. All right, this style is a little bit more straightforward in that we've got just a set of reagents that we're going to basically do in order to make this work. So we're going to, what I would do here is I would kind of draw it out in steps so that we can really see what's going on, so that I can see what's going on as I'm trying to work through this problem. So first we add that sodium amide base, which is going to deprotonate the alkyne. And then we're going to methylate that. Right, and then we're basically going to deprotonate the other side. Following this thing around. Methylate that side also. And then finally, we can reduce this to the cis alkene. So the best answer here is the cis alkene, however you draw that. As we talked about, and this comes up a lot in this test just because it's really useful with the reactions that we know so far, this Lindlar's catalyst gives us the the alkene instead of reducing all the way down to the alkene. All right, which of the following is most reactive to SN2? So what kind of a substrate favors SN2? Here we're looking for a good leaving group and a primary substrate would be the best for SN2, something very open. So the best for both of those is 1-bromobutane. Just look at the, if we look at these structures, so there's 1-chlorobutane, 2-chlorobutane, and then we could replace those with bromine. So this one's the most open, right? We can do the substitution there. This one's a little bit more hindered. Bromine is a better leaving group than chlorine, and so the better leaving group gives you faster SN2 reaction. If we look at SN1 instead, we still want a good leaving group. We still want the best leaving group, but in this case, all the leaving groups are the same. 1-chloro, 2-methylbutane, that's primary substrate, that's not going to be great. 2-chloro, 2-methylbutane, tertiary, that's looking pretty good. 2-chloro, 3-methyl, again, a secondary, it could happen, but not as well. And then 2-chlorobutane, right, would be about the same. So this is the best one, which would give it that tertiary substrate. All right. So now when I'm asking for a curved arrow mechanism, I'm showing you specifically what is happening, like what reaction is happening. So we're starting with 2-chloro-2-methylbutane, exactly what, right, a good SN1 substrate. And then in this case, we're not doing the SN1, we're doing the E1. So yes, if you did this reaction in a beaker or whatever, you would get a mixture of SN1 and E1 products. But in this case, I'm specifically telling you only do the E1. I'm showing you what to do. When I ask you for a mechanism and I give you the product, I want you to show me how do we get from here to here, step by step, with the arrows. And this is another thing where if you're doing this exam or a quiz or whatever, you can look this up and you can look up, well, you can't look up specifically this reaction, but you can look up other comparable reactions and use that to guide you. So in an SN1 reaction, or I'm sorry, in an E1 reaction, you first get rid of the leaving group, so the leaving group leaves. Sorry if you hear some jingling, my dog is here. Then we have hydrogens here. And the base we're using in this case is the water. So the water can deprotonate this, which is the second step of the E1. So that's the elimination part, and then we're left with some hydronium and chloride. But that's it. That's the whole question. I just wanted you to know those two steps of an E1 reaction. A lot of people did a lot of other stuff, got some SN2, SN1 reactions, got some other random stuff going on. All you got to do is show the steps to get from the reactant to the product. All right. Okay, so D and E here are a couple different ways of evaluating questions, but D is about like looking at the conditions of the reaction, and then E is looking at what's the product, because the solvent and the temperature are unknown. So first, this one's kind of using the strategies that we talked about more, where we look at, okay, bromoethane becomes ethanol upon treatment with hydroxide ion. So bromoethane is this, and then ethanol is this. So clearly we're doing substitution there. ER is leaving, OH is coming in. We got to think about SN1 versus SN2. In this case, if it's hydroxide, That's a really strong nucleophile on a primary substrate, so we're definitely looking at SN2. Then 1-methyl-1-cyclohexanol reacts with water and acid to form 1-methyl-cyclohexene. Again, I would write these out if you didn't. And this was one where I was kind of expecting you to take advantage of the resources that you had, because this is not one that we've really talked about with alkyl halides. So in this case, you've got something else going on, but it's clearly still an elimination reaction. So if you look up elimination reactions with OH leaving groups, because OH is such a bad leaving group by itself because it's a strong base, it needs something like to be protonated to become a good leaving group. So we'll talk about this mechanism probably on Wednesday. But you would find that this ends up being E1. So you've got a tertiary substrate that becomes an alkene, regardless of whether or not you know that reaction. If a tertiary substrate is becoming an alkene, that's going to be an E1 type mechanism. All right, so propyne, which is that, becomes propane in the presence of hydrogen and metal catalyst. So we talked about that as reduction, but it's really also addition, alkene addition, just like all of the reactions in chapter, what is that, 5? Chapter 5, yeah, the alkyne chapter. Those are all addition reactions. So we're adding hydrogen across the double bond. That's addition. And then iodopropane, 1-iodopropane, reacts with potassium terbutoxide. In this case, I didn't tell you the products, but we have this big, strong, bulky base that we looked at before that's always basically going to do E2. So whenever you see a big, strong base like that, we're always going to assume that's going to do an E2 reaction. It's just too big to substitute for anything, really. It's going to deprotonate first. It's a strong base. So that's what's going on there. All right, any questions about those? All right, so this one, the issues I had with this one is that a lot of people kind of use the same logic as these previous ones to try to come up with the answer. So let's take a look at the substrate. 1R, 3S, 1-bromo, 3-methyl cyclopentane. So that looks like this. Okay. And so the question is, how the reaction conditions are unknown. We don't know anything about this except that it's reacting with sodium chloride. And the reason that I said that in here, or the reason that this is a different, oh, it's blurry. Is it blurry for everybody? Or does it just depend on your connection? I wonder if my upload thing is blurry. It's a little bit blurry. All right, I can make it bigger, but then we have the same issue of not seeing the, oops, not seeing the ends. Back to where we were here. Can you see the edge of the question here if it's like this, or is this cut off? Better? Okay. Okay. I'll try to troubleshoot that. Okay, so we've got this. Where was I? Oh, yeah. So the reason that this was set up the way it is this reaction could be SN1 or SN2 because we've got a secondary substrate and we've got a like medium nucleophile. It's a little bit cut off. Where does it cut off? Is it the edge of the writing or? maybe I can like, just make sure I write like over on this side more or something. Okay, you can see it now. Okay. Okay. Good. All right. So the idea is that that with what you've been told so far, this could go either way. It could go SN1 or SN2. There's no way of being able to make that distinction from just looking at the substrate and the nucleophile. That's the idea. You can't tell from those things. So the only way that you could tell this is by analyzing the product. How could you look at the product and figure out if the reaction was SN1 or SN2? And the answer is that if the product were SN2, it would be uh, stereo selective, meaning that the Cl would invert the configuration and we have this SN2 product. And we should only have that product. If we did SN1, then because of the carbocation that's formed, we would expect to get this product and this product. Because it goes through that carbocation intermediate, we lose the stereochemical configuration of that reaction, and we end up with both possible configurations. So it's a mixture of diastereomers. My head's blocking that. I can see that. Okay. So you end up with a mixture of diastereomers there instead. So that's how you would tell the product. If you got a single stereoisomer or if you got a mixture of diastereomers, that's how you could tell if it was SN2 or SN1. Most people, I would say, in this question answered it just like D, where they looked at the substrate and the nucleophile. But with this particular question, without knowing other conditions, you really can't make that distinction here. All right. Many of you recognize that this is very similar to the reaction that we did in lab, or the experiment we did in lab, the acid-base separation. So what you would recognize here is that this is just a regular neutral organic compound. This one is an acid. So if we put this in base, let's see how we can try this. If we put it like in sodium hydroxide solution, it's going to undergo an acid-base reaction and get deprotonated and form the sodium salt. So this is now soluble in water. Which is exactly what we did in that experiment. We took something that was an acid, a carboxylic acid, and actually in the experiment, I believe, it was an acid and a base, not an acid and a neutral, but same idea. You can take an acid, you can deprotonate it, and you can make something soluble in water. So now this is going to stay in the, this one, A, will stay in the organic portion. If we imagine a separatory funnel, we'll have two layers. So we've got like a blue layer and a red layer. So if this is our organic layer, like ether, A will be in there. And then we could have B in here with the sodium hydroxide. I know that's small. It probably is so hard for some of you to see. It just got really blurry. So that's either my fault for my internet being too slow or your fault for your internet being too slow. I don't know. But I will post this also so you can go back and check the, actually, you know what? I think I can do this right now. Let me resave this. I'm going to put it in our notes folder that's linked on Blackboard. Oh, I can't do it like that. Internet going back and forth. So if I I'll do this anyway, just in case it happens again. If I'm going to save this in our notes folder, and that's going to make it so that you can get it just where you get our notes. And then as I write on it and save it, it'll update. So you'll get the latest one. So if you want to actually see the document, you can do that. All right, so where were we? So these are now separated. So then you would take out the bottom layer. Okay, so let's say we took out the bottom layer B. So what's actually in there? Well, actually in there right now is sodium and water, of course, and B, the deprotonated version of B. So then the next step would be to reprotonate this so that it's not soluble anymore. Experiment is these organic acids, when they're neutral, they are not soluble in water, but when they're charged, they're soluble in water. So you can charge them by either adding acid or base so that they go into aqueous solution, and then you can neutralize them. So we would neutralize this with HCl or H2SO4 or whatever. We neutralize it, and then it's going to precipitate out of solution when it's back to neutral because it's no longer soluble in water. And that's how we would separate it. So then you could collect this. And then to collect A from the ether layer, since you can't really protonate it or deprotonate it, you would just take that ether layer out and rotovap it down. And then you'd have this isolated back out. So you just get the ether out of it or just let the ether evaporate in the hood or whatever. So that would be the full best answer. I would say nobody got quite there. So I was fairly lenient. If you said something about the idea of proton transfers, that if you deprotonate this, it's going to dissolve in water, and then you reprotonate it, and it's going to precipitate. That's really the important part. That's what I was looking for. If you said things like you can separate these by sublimation or by distillation, that is not quite right because I don't know that it's true. If you find references for those, and it is actually possible to do that based on their properties, and you want to send me those, I will give you credit for them, because if that is indeed a legit way to separate them, that's fine. But I don't think it is just looking at those structures. Let me check this thing. So if you have a second to, where did my controls go? If you have a second to look, see if you can access this exam copy in Blackboard in the notes folder, and then you can look at it and have it ready for you. Okay, sorry about that. So if you've got that, all right, so let's move on. Okay, so this one should have been fairly straightforward. You just look up the pKa's of the two acids, and whichever side has the higher pKa's, that's the side that's favored. So you got acid versus acid, right? Whichever one loses its hydrogen is acting as an acid. And we'll do both of these together. So in this case, you've got the same molecule as this, so that could be a little bit confusing. But again, look at what's happening. This is losing its hydrogen. And so this is the other acid. So to find those pKa's, you may not find these exact molecules, but we should be able to find something similar. So let's jump down to our pKa table. Okay, so we do actually have this exact one. So we've got benzoic acid. And then we've got, let's see, what else can we find here? We need to find an amine. So we got this one. And this is about 36. And then there was an alcohol somewhere in there too, right? So we can look at an alcohol at about 17. And yeah. Oh, here's another ammonium. So a non aromatic ammonium is probably a better fix here. So we'll look at let's look at this one. 10.6. All right, so going back up. Oops. So for this one, we've got about, we'll say about 11. It was like 10.6 or something. And this one, again, it's a little bit, or it's benzoic. Let's try to find a better one there. Right. So actually, oh, there it is. I'm just realizing now that I don't have a good comparable alcohol for that one. Oh, no, that's not 11 because that should be charged. Sorry. Yeah, that's okay. So that's the problem. So we need a neutral amine, not a charged one, to compare against. So that's that 36. Sorry, I'm confusing myself here. Now it's being slow also. Okay, sorry. So looking, I don't know why I jumped to this bottom one. This should not be 11. This should be 36. That's why I confused myself, because this is the one that would be about 11, being NH3 plus. So anyway, sorry to confuse you. We'll stick with this bottom one first, I guess. So this is about 36, and an alcohol is going to be about 15 or 16, just like water. Whoa, why is that moving? It's not moving. It's not moving. Okay, about 15. So however you find it, this one is the higher pKa's, so that's going to be our favorite side. And then the first one, we've got about 11 here versus, what did we say that carboxylic acid was about 4 or 5, right? So the left side is also favored here. Okay, so you just find pKa's, and whichever side has the higher pKa's, that's what you go with. All right. Any questions there? All right. I actually have to stop now. I have to help my kids with their school stuff starting at 10:30 today. So I'm going to stop there. We'll continue this on Wednesday. Again, I will get more stuff off on Blackboard for you to turn in the parts of the project, and then keep working on the quiz 8. And let me know if you want to meet at any time, and I will find some time to meet with you. I will also be sending out a poll, so watch for that for some more permanent office hour time suggestions. So hope you all stay healthy, and let me know if you need anything. And hopefully I'll see you on Wednesday or before. So thanks, everybody. Bye.